distribution. Okay, I told you the other time, if we really want to understand our environment, whether political, economic, or medical environment, of course, we need to I understand the probability of distribution of whatever variable of interest. Now, when we exponential distribution actually belong to the family of a continuous probability distribution, and is being used, to model the waiting time, before the occurrence of an event. I'm going to say that again. The waiting time, okay? Uh, exponential exponential distribution. Okay, so this actually model, okay, waiting time, okay, before before the occurrence, okay, of an event. Okay, now the waiting time before the occurrence of an event, this has a lot of application across. You may want to talk about how long are we, maybe your laptop has an issue and you take it to a tech. So how long are you going to wait before the laptop is going to be fixed? Or you can talk about the occurrence of bank failure. How long are we going to wait before the bank will record what I call a significant default that could lead to bank failure. So if you really want to answer questions like that, we actually going to use exponential distribution. Okay, so I'm going to say when x follow exponential with a parameter beta, okay, f of s equal 1 over beta exponential raised to power this, s greater than 0 and beta greater than 0. So in this distribution, the parameter is beta, okay, and that parameter is called scale parameter, so beta here is a scale, okay, it's called scale parameter, okay, and what does that actually mean? The scale parameter actually will enable us to understand how spread, okay, the distribution that we how spread the data that follow this particular distribution. Okay, the beta has to be greater than 0, it has to be non-negative, and x also has to be non-negative. Okay, just like what we've been doing, we may also want to find what is the expectation of x, okay, and what is the variance, okay. So the expectation of x, like on average, how long am I going to wait on average? That's what it means. And the moment average is involved, variance is going to be involved. Okay, so that is what you can see being displayed. Of course, like I said on Friday, I'm going to walk you through some, example. Okay, take a look at example 6.21. Here says, suppose that the time in hours required to repair a heat pump is that. So you need to be given the parameter. Okay, when you have the parameter, we can actually use this distribution to figure out what is the probability of at most one. Well, what we're just going to do is to integrate. We're going to perform an antiderivative. Okay, so like I said, I'm going to walk you through that. But what I want to do today is showing you, okay, how the mean equal to that and the variance equal to that. Okay, so if you want to, derive this, I will advise that you actually use the method of moment generating function. Okay, so mx of t, okay, is expectation of this, okay, and which is going to be 0 to infinity e raised to power that f of s dx. Okay, so right now, so 0 to infinity e raised to power that, the f of x is 1 over beta exponential raised to power that ds. Okay, so this guy is a constant, right? I can bring it out. So got is 0 to infinity. Then I'm actually going to combine this guy. I'm going to have ts minus x over beta ds. So here I can do 1 over beta, 0 to infinity. I'll actually have this guy here. So 1 over beta minus t ds. Is there any question about how I simplify this? Is there any question on that? Okay, you good, right? Okay, so what you just need to do is I can integrate this guy now. It's gonna be super cool. So expected, oh sorry, the moment generating function now. Okay, the moment generating function now. Okay, the moment generating function now. Okay, so if I want to integrate this guy and an exponential function, I'm actually going to concentrate on the exponent. Okay, I'm actually going to block this guy, then we differentiate the exponent with respect to x, and that's going to be negative, this guy. Okay, so here I'm actually going to have this divided by negative into this. Then I'm going to put this. Is there any question on that? That's super cool, right? That's antiderivative. Okay, so the moment I actually have this guy now, okay, so don't forget there's a minus here, right? Okay, so I'm going to plug in infinity, okay, plug in infinity, okay, divided by this, okay, minus, so plus another minus, you're gonna have a plus, right? Then you're gonna plug in 0, okay, plug in 0, okay, divided by 1 over that, okay, exponential is about negative infinity, the whole of that should be equal to 0, okay, I want to talk about the rate of decay, okay, so if this is gonna be 0, I'm actually gonna have this into, okay, there's going to be 1 divided by 1 over that. Okay, so I can use my beta to multiply that. Okay, so I'm actually going to say, so there's going to be 1 minus beta t. So what I'm trying to tell you now, okay, the moment generating function, okay, of an exponential distribution, okay, it's actually what you see here. Okay, so this is a moment generating function of exponential distribution. If I want to know if this guy is right, you know what I'm going to do? I'm going to plug in 0 wherever I see t, right? When I plug in 0 here, so this is going to be 1, okay? Now, if I want to if I want to find the expected value of x, don't forget, expected value of x from the moment generated function is actually going to be m prime x of 0. Okay, so what is my m prime x of t? I need to get my f as, I want to differentiate this. This is a composite function, right? Okay, negative 1, okay, negative 1 coming down, differentiating side with respect to t, that's a negative beta. Then I'm actually going to have 1 minus that, it's a power negative 2. Okay, so I'm going to plug in 0 now. Okay, plug in 0 now. Okay, plug in 0 now. That's going to be beta, right? It's going to be, okay, raised to power that, right? So it's going to be that, so 1. So that's going to be beta. And this guy here is actually expectation of s. So that is how we prove, okay, that the expected value of s, which is the same thing as the mu, is actually beta. Okay. Now, similarly, I'm not going to waste my time on the variance. I'm just going to give you a clue. Okay. If you want to, is there any question moving forward? You're good, right? Okay. Now, if I want to derive the variance, okay, if I want to derive the variance, don't forget, the variance of s is expectation of s squared minus expected value of x all squared. if you want to use a moment generating function, it's going to be m prime prime, okay, x of 0 minus m prime x of 0 all squared in terms of moment generating function. So, and you know you've already gotten this guy. We just square that. Okay, now you need to get this guy. You need to obtain m prime prime x of t. Okay, now you get your m prime prime s of t from here. If you take a look at this, if when I simplify that, it is this guy, right? Now I need to differentiate that guy. -2, okay, minus beta is going to come out. That should be 2 beta squared, right? Okay, so it's going to be 2 beta squared into 1 minus this raised to power that. Okay, so don't forget expectation of s squared is m prime prime x of 0, 2 beta squared, 1 minus that raised to power that. So this is going to be 2 beta squared. So that is your expectation of s squared. Of course, the moment you have that, of course, so you can, if you plug this guy here, which is going to be 2 beta squared minus this whatever value of s that you got, that's a beta squared. So what do you have? That is your variance. Okay? So, and of course, your standard deviation is going to be the square root of that. Is there any question before moving forward? You're super cool, right? Okay. You know, do not hide your feelings. If you don't understand, please ask me a question. Okay? Now, you can see all these examples. I'm actually going to reserve them for Friday, okay? So, but the moment you understand the formula, all these are they're going to be so easy. And I want to believe you've come across all of this before in your high school. You know, take a look at this guy. You've come across then, but you may not know the essence. Okay, they are all kind of exponential function. Okay, okay. Now I want to go into another distribution that will